Now I am recording. All right, thank you. So just for the people joining in the recording, God, I didn't record any of my announcements, but I'll kind of send out an announcement later that covers all that material, so you don't have to hear it again. Right now we're just working problems. Find the area between these enclosed between these two curves. Y equals x squared minus 6. Y equals 12 minus x squared. My one suggestion that I want to reiterate is to always try and give a rough drawing of these curves just to get an idea of what they look like. So I draw 12 minus x squared and I get this upward facing parabola. Or I do 12 minus x squared, I get this downward facing parabola. I do x squared minus 6 and I get this upward facing parabola. I can see that they're going to intersect at 2 points here and here, but I don't know where those points are. So that's my first problem, to find those 2 points. So I set my curves equal to each other. And then an important thing to note is that if it's something simple like x squared equals x, I don't want to just solve for x just by dividing by x on both sides. I want to move everything over to one side and get a polynomial. So I move everything over to one side of my equation, let's say the left side, and I get this. Okay. And now I want to solve my polynomial. Okay, I want to factor my polynomial. Okay, so I can divide everything by 2. So I get x squared minus 9 equals 0. So I can factor this as x minus 3 and x plus 3. So my solutions are x equals positive 3, x equals negative 3. So that means my curve should intersect at negative 3 and positive 3, which tells me I need to integrate from negative 3 to positive 3. And what am I integrating? I want to do top curve minus bottom curve. So what's the top curve? This guy. What's the bottom curve? This guy. Be sure to distribute your negatives. Okay, so this integral becomes negative 3 to positive 3. 18 minus 2x squared dx. And this should evaluate to 72. Okay. So a lot of, maybe I'll skip a lot of steps on these problems if it's pretty basic. Like, for example, from here, I think the answer is pretty clear, or the steps are pretty clear. Nothing really revolutionary going on there. So the important things I want to note are, okay, when we're solving for these points, we move everything over to one side of the equation and factor. Okay, that's the best way to do this to find our points of intersection. Okay, let's try another one. This is, I think, a good example of why we kind of do that process. So let's find the area enclosed by the curves y equals x cubed, y equals x. Okay, so again, getting a rough drawing of what's going on is really helpful. So y equals x cubed looks like this. Y equals x should look like that. So this area is divided into 2 pieces, right? I got this shaded region and this shaded region. So I might need to do 2 integrals, okay? Because let's see, in this left piece, y equals x cubed is on top, and on this right piece, y equals x is on top, okay? So that's telling me I need to divide this into 2 different integrals. First thing is I need to find all these points of intersection, okay? So where my curves intersect each other. How do I do that? Again, I set one curve equal to each another, and then move everything to one side and solve my polynomial. Okay, so these are my points of intersection. my curves intersect at x equals -1, x equals 0, x equals +1. Okay. So looking at this point that I now know as x equals -1 to 0, x cubed is on top. So that section should have the solution, or excuse me, the area should be given by -1 to 0, x cubed minus x dx. And then the right piece should have this integral, x minus x cubed dx. Okay. So I need to divide my problem up into two integrals, solve both of those to get my area. And again, I think here it's pretty straightforward. I'm not going to solve through the integrals to get the actual answer. You guys can do that on your own. So that's it for 6.1. There are varying levels of difficulty, obviously. Anybody have any questions in particular on 6.1? You can indicate that in the chat or chime in if you like. Okay, I don't see anything. So I will move on to 6.2. All right, so 6.2 and 6.3 are areas of revolution, right? All right, areas, or are we doing, yeah, it should be areas, right? No, volumes. Okay. Yeah. Okay. So 6.2, problem 7. Let's start with that one. We are given y equals x cubed, y equals x, and we're told to rotate. We're told to find the volume of objects when we rotate the region enclosed by these curves around rotated around x-axis. So again, first step, drawing our region, okay, our initial region. Y equals x cubed. Oh, and let's see, we want x greater than or equal to 0. Okay, so when we have this extra condition, x greater than or equal to 0, my region just looks like it's this shaded region. And then I'm rotating it around the x-axis. Okay, so I get this thing. And then my object is the washers, right? That I get from, it's kind of like a cone with some empty space in the middle. And my cross sections are these washers. Okay. So remember our formula. When I've rotated around the x-axis, and I have washers, I'm going to do pi RO squared minus pi RI squared. Okay. Let's see, if I rotate around the x-axis, everything's going to be in terms of x, right? So I want to integrate in terms of x, and then I have my bounds a to b. So I need to figure out what information do I need. I need to figure out my bounds, and I need to find out my radii. I always measure my radii from the line I'm rotating around. Okay, so in this case, we're rotating around the x-axis. So my radius needs to be measured from the x-axis to my outer curve. That would be my outer radius. And then x-axis to my inner curve. That would be my inner radius. My outer curve is going to be given by this line, right? X. So my outer radius should just be X. My inner radius should be X cubed. Okay, so my to the cloud. Okay. Let me just make sure this is okay. So I'm still sharing screen. All right. So if no other questions, I will move on to, well, I'll do another problem from 6-2. A couple more problems. Okay. We might also rotate around a different axis, right? So we need to make sure we are setting up our problem correctly. So let's look at the problem. We want to find the volume of the region when we rotate the curve, the area enclosed by y squared equals x, x equals 2y, and we want to rotate that region around the y-axis. So again, let's try and draw our region. Okay, y squared equals x is this sideways parabola. X equals 2y, well, that's the same as 1/2 x equals y. So that should be this kind of, this line with slope 1/2. Okay, so my region is this, and then I'm rotating it around the y-axis. Okay, so I rotate it around the y-axis, and I get something like this. Okay, so I'm dealing with washers again. Okay, so my object is kind of a cone. My cross sections are washers. All right. So again, let's find where our curves intersect. That's always going to be part of our problem. How do I do that? I set y squared equal to 2y and solve. I bring everything over to one side. This has solutions y equals 0, y equals 2. Okay. So those are going to be my bounds of integration. And let's see, I've rotated around the y-axis, so I want to do everything in terms of y. What's my outer radius? Okay, so I'm measuring my radius from, let's clean this up a bit. I'm measuring my outer radius from the line I'm rotating around, the y-axis. It's my outer curve, which is x equals 2y. So I want RO equal to 2y and RI equal to y squared. Okay, so my integral should be pi 2y squared minus pi y squared squared dy. Simplifying that, I can bring my pi outside. I should get this antiderivative, and that should evaluate to, I believe, 64/15 pi. Any questions? Let me just check Zoom. Okay, no questions. Let me see if my computer's back online. It is not. All right, so I will continue on the iPad. Let's try one more problem, one or two more problems from 6-2. This is a good one. We also need to be able to figure out our problems when we're not rotating around an axis, okay? Everything's easier when we're rotating around the X or Y axis. What if we take the region enclosed by y equals x squared, x equals y squared, and rotate around y equals 1. First step, draw on our region. Y equals x squared is just our normal parabola. X equals y squared is our sideways parabola. So this is our region. And then let's see, we could figure out first where these curves intersect, okay? Maybe right away you can see they should intersect at 0, 0, 0, and 1, 1, okay? And then we're rotating around the line y equals 1, okay? So we rotate and we get this region up here, and then our object is kind of a cone with these washer cross sections. Okay. So what's our outer radius? Again, I'm measuring from the line I'm rotating around, which in this case is this line y equals 1. Okay. So what's my outer radius? It's the distance from y equals 1 to this curve, or I could also measure it, which might be easier, from the line I'm rotating around down to this curve, right? That would also be my outer radius. And if I measure downward, I can use my original equation for my function, okay? So this curve here is y equals x squared, right? So my outer radius should be 1 minus x squared. What's my inner radius? Okay, it's the distance from it's the distance from the line y equals 1 measured to my inner curve. So just that distance right there. That inner curve is x equals y squared. Since I'm rotating around a horizontal line, I want to do everything in terms of x. So I should consider this curve, instead of x equals y squared, I should consider it as square root of x equals y. So my inner radius should be 1 minus square root of x. Okay. And then I should use 0 to 1 as my bounds of integration. So this should be my integral. Solving that, distributing everything, I should get okay, so once I square everything and simplify, I should get this integral, which should simplify as (11 pi over 30). Okay. Any questions? Let me check the Zoom.
Okay, no questions. Does anybody need to be admitted? Okay. One more from section 6.2, then we can move on to section 6.3. How about volume of the region enclosed, or the volume of the region we get when we take the area enclosed by y equals x cubed, y equals 1, x equals 2, and rotate around the line y equals -3. Okay, so let's draw our region. Y equals x cubed looks something like this. Y equals 1, okay, should just be that line there. X equals 2 should be this line here. Okay. So maybe some of the difficulty people have is figuring out which region we're talking about when we say the region enclosed by these three curves. So only bound the region by the curves we're given. So if I was looking at this, maybe some of you guys might think, okay, well, this is the region, right? Okay, but you've kind of subconsciously used the x-axis as a bound, and they don't tell us anywhere to use the x-axis as a bound up here, right? So actually, if we use that region, it's unbounded below, and the shaded region would just continue on forever, right? It would be everything down here, so it'd continue on forever. So the only possibility we have for a finite region is not this, it's actually this region, okay? So it's bounded below by this line y equals 1, to the right by this line x equals 2, and above by y equals x cubed, okay? And then we rotate that around the line y equals -3, right? Which is all the way down here. Okay, so we rotate it around that line, and what do we get? We get another piece of our curve down here. Okay, so this is our object, and let's see, it's connected by all these washers. Our object is a kind of cone looking thing. Okay, so this is our region. First thing I need to do is, well, let's see, our region, our curves intersect here, here, and here, right? I need to figure out what all those points are. This one's easy to find. It's where, let's see, it's where this line y equals 1 intersects our curve x cubed. Okay, so we say, where does 1 equal x cubed when x equals 1? Okay, what about this point here? That's where our line y equals 1 hits the point x equals 2. That's just when x equals 2. Okay. And what about where these curves meet? Okay, this is where the point x equals 2 hits the curve y equals x cubed. How do I figure that out? Well, I just plug in, let's see, the x value of this point has to be 2, right? So I just plug 2 into that point. And actually, we don't even really need this, but if we wanted to, we could figure out this is the point 2, 8. Okay, so now I know all the bounds of my region. Now I need to figure out my outer radius, inner radius. Okay, outer radius, again, I'm measuring from the line I'm rotating around, which in this case is y equals -3. Okay, and let's go back up to our original region. So outer radius would be the distance from here to this top curve here. Okay, so what is that radius? Let's see, it would be the y coordinate of this curve. okay, if the y-coordinate is the distance from here to the x-axis, and then we got another 3 units downward, right? We can consider this as, we could do the y-coordinate of our curve, which is x cubed minus whatever y-coordinate this is, which is, in this case, -3. So x cubed plus 3 is our outer radius. Inner radius, okay, that's going to be the distance from, let's see, clean this up a bit. Inner radius is going to be the distance from my line y equals -3 to here. Okay, so what is that distance? That's always the same. It's always the distance between y equals -3 and y equals 1. Okay, so that's going to be, let's see, y equals 1 minus y equals -3 equals 4. Okay, and then where am I integrating? I'm integrating where my object exists. So from this x value to this x value, this we said was x equals 1. This is the line x equals 2. So I want to integrate from 1 to 2 pi x cubed plus 3 squared minus pi 4 squared dx. Simplifying, I should have this integral, and you guys can take it from there. That should give me my solution. So this one's a bit more complicated. So what I would suggest is just be careful when you're figuring out what region they're actually talking about. Don't, use only the data you're given. Don't kind of add your own assumptions about where your bounds of your region are. And then it's just a matter of measuring radius from the line we're rotating around and squaring that properly. Okay. Any questions? Okay, with that, we can move on to section 6.3. And let me take another minute to see if my Zoom on my computer will work again. Dum dum dum. Yeah, okay. So I'm gonna just take a minute to restart the Zoom on my computer.
All right, can you? No. All right, can everybody hear me? Can anybody hear me?
Yes, everything's all good.
Okay, good. Sorry about the technical difficulties. It's a learning process. All right, so section 6.3, again, we're finding volumes. Now we're using different formula. Now we're using cylindrical shells. So we want to use the formula. Let's see. Okay, so if we're doing everything in terms of x, we would, for example, use the formula 2 pi x f of x dx on our bounds of integration. Okay. So let's try an easy example first. Let's try and find the area of or the volume of the region we get when we take, let's see, y equals, how about y equals x to the 3/2, y equals 8, x equals 0. Okay, so let's find this area. Okay, so again, first step, no matter what method we're using, trying to, no matter what method we're using, we should draw our region first. And we're going to rotate this around x-axis. All right, so let's draw our region. X equals 3/2. That should be somewhat, kind of a parabola. Not quite x squared. Okay, y equals 8. That would be just this line up here. And then x equals 0. Okay, so we want to be bounded by this. So our only choice for this region is this thing. And then we're rotating around the x-axis. Okay. So we get this. And our cross section should be these. Oh, this is wrong. Our cross section should be these washers. Okay. So remember that this, we kind of use an opposite rule for cylindrical shells. If I rotate around a horizontal line, I want to do everything I want to integrate in terms of y. Okay. So let's see, I need the formula 2 pi y fy dy. Okay, so where am I integrating? I always integrate from my center outward in one direction. So let's see, I could integrate from 0 to this line here, which is 8 in this case. Okay. Y, that's going to stay the same. F of y. What's my f of y for my outer, what's the f of y for my cylinder? Okay, that's actually going to be the distance from the bottom of my object to the top of my object, kind of measured this way. So in this, the cross sections are these washers, but really that's not what's important, right? We're making cylinders. So for this method, we're making cylinders. So what do my cylinders look like? Okay, so this cylinder, for example, would be would look like this, right? Okay, so the height of, let's see, this is my y coordinate, kind of the radius of my cylinder, and then this f of y is going to be the height of my cylinder measured from here to here. Okay, so what is this distance? It's the distance from my x-axis to my curve, which is x equals 3 over 2. And I want to get that in terms of y, right? So if I have y equals x to the 3 over 2, what is my function of y? I should have y, y to the 2/3 equals x. Okay. So my integral should be 0 to 8, 2 pi y times y to the 2/3 dy. Let's just simplify our integral, pull out the 2 pi. Okay, I get y to the power of 5/3. I integrate. Okay, I'll kind of go through and actually try and find the numerical value. Okay, y to the 8/3. If I plug 8 into that, that would be messy. But I could think of this as y to the 1/3 to the power of 8. Okay, so I plug 8 into this. What's 1/3? 8 to the power of 1/3. So cube root of 8, that's just 2. Okay, so I got 2 to the power of 8 minus, and then my other one's just going to be 0. So I have 3 pi over 4, 2 to the power 8. And then that should be fairly easy to find. Let's see. 4 would be 16. So 32, 64, 128, 256 divided by 4. That's 64 times 3. So it should be like 64 times 3 pi, which would be what, 128, 32, 192 pi, I think. So let's check the back of the book real quick. This was number 11. Yes. Okay. Any questions? All right.
Yes, I have one question. I'm sorry. Now with this problem, I'm assuming that cylindrical shells is the only way to solve it.
Yeah, so let's see. So sometimes that is the case, that we can only solve it one way or the other. Sometimes we could solve it either way. So looking at this, if we had our same region, let's see if anything goes wrong. Okay, we have this region. Okay, if we tried to do discs and washers, let's see, our outer radius would be this thing. Okay, so that's fine. Inner radius would be this. Actually, no, I think you could probably do this either way. So we could try it real quick. Our outer radius would just be 8. Our inner radius would be x to 3/2, and then okay, yeah, x to 3/2. Okay, so if we did cylindrical shells, and then let's see, this is 0. The question is, okay, where does x to the 3/2 equal y equals 8. So where does this equal 8? Should be 4. So it should be 0 to 4 pi 64 minus pi x cubed dx. Yeah, I think it should be fine. Let's see. 4 to the 4th would be 256. Yeah, 256 over 4. So really it's pi times 4 times 256. Yeah, it should be the same thing. So this one you could solve either way.
Gotcha.
But yeah, there will be some of them where we can't solve them either way. That would usually be, let's see.
Say if at a point the disc and washers would fail.
Yeah, there are circumstances where discs and washers would be. Oh yeah, so here's a good example. Let's say we had a curve like this, and we rotated around the y-axis. Okay, so we would get an object like this. If we tried discs and washers, right, the washer would look like this. The outer radius and the inner radius would be coming from the same curve, which wouldn't work out. So this one, we would need to use cylinders instead. Okay, so that's a good criteria for when to use one or the other. If the outer radius and inner radius are coming from same function, we should definitely use cylinders.
Understood.
Okay. As far as difficulty, I'd say that one is fairly standard. It's not too hard or too easy for the final. I would suggest for all of these, you know how to find these volumes when our region is centered around a axis, like the X and the Y axis, and also know how to solve these problems when we're rotating a region around some other line, like X equals 2 or Y equals -1, something like that. And then that should cover all possibilities for those. Any further questions on chapter 6? Okay. If there are no further questions, I'll kind of end it there. And we'll pick up with chapter 7 review tomorrow. Okay. So I'll stick around for a few minutes. If you guys want to stick around and ask me questions or anything, I'll give it another 5 minutes or so and see you tomorrow if not.
Thank you, Professor Dunn.
No problem. 2 to 3 tomorrow. Yeah, I'll just keep the same time every day just to be consistent. Review will be 2 to 3.